This conference will now be recorded.
So very good evening, students. Today we are starting discussions on magnetism. So in these classes on this particular topic, what we are going to do is we are picking up JEE Advanced questions and we'll try to solve those with proper logic and concept. So let us first discuss this question. So as you people know that sometime in the JEE Advanced question there will be passage given, and depending on the passage there will be questions. Okay, so this is actually passage based question, and sometime on the same passage there will be multiple questions. Like here also there are two questions on this passage. We'll see what are those. Okay, let us first read this passage itself. The passage says, the figure shows a circular loop of radius a. As you see in the figure, this is a circular loop of wire with radius a with two long parallel wires, number 1 and 2. There are two parallel, and see these are dotted. PQ and RS, these are actually the two wires, parallel wires, as you see, and they are named as PQ is named as wire 1 and RS is named as wire 2. And these dots or broken lines at the ends of the wires indicate the wires are infinite in length. That is what is indicated by these broken lines. Now the figure shows a circular loop of radius a with two long parallel wires, number 1 and 2, all in the plane of the paper. All, that means this one, these wires, all are in the plane of the paper. The distance between each wire from the center of the loop is d. As you see, this is the center of the loop, and from center of the loop the distance of each wire is d. And you can see here this d in this case actually is greater than a. So that is what we can see here. Okay, the loop and the wires are carrying same current. See, the loop is carrying current, sorry, loop is carrying current I, this is also carrying current I, this is also carrying current I. So all of them are carrying current, same current, but direction of the current for this loop is only given. Current direction along these two PQ and RS wires are not given. The current in the loop is in the counterclockwise direction if seen from above. Okay, so suppose you have this loop, you are seeing from top. Okay, so this loop is actually in the plane of the paper, so you are looking from here. Okay, so if you look from above, then what happens? It shows that the current is in the anti-clockwise direction. So you may know what will be the direction of the magnetic field produced by this if we require. You know the right hand thumb rule for loops. Okay, right hand thumb rule for the loop. So the current actually, if it is anti-clockwise direction, then it will be upward direction. Okay, that is what we can understand. So it will be in the upward direction. That means it is going, since it is in the plane of the paper, so the current, sorry, magnetic field produced by this loop will be in the direction which is perpendicular to the plane of the loop. okay, or that is actually upward direction, or it is coming out of the plane of the paper. So that is what we can understand from this particular statement. Now the question is, see there is a question. Question is that when D is nearly equal to A but wires are not touching the loop. See, when this and A D and A are nearly equal. D and A are nearly equal. When D and A are nearly equal but not touching the loop, it is found that the net magnetic field on the axis of the loop is zero at a height above, at a height h above the loop. In that case, the question is, in that case, currents in wire 1 and current in wire 2 are in the same direction. Okay, so current, first option, current in wire 1, current in wire 1 and wire 2 are in the same direction, in the direction PQ and RS respectively, and H is equal to A. Okay, the second option is the current in the wire 1. Option B says current in wire 1 and wire 2 are in the direction directions, it's through directions PQ, directions PQ and SR respectively, when is equal to H is nearly equal to A. Option C says the current in wire 1, I'm just writing the same statement, current in wire W1 and wire W2 are in the direction directions PQ and SR respectively, H is equal to 1.2a. And the last option I'll write it to here. Current in wire 1 and wire 2 are in the directions PQ and RS. PQ and RS respectively, and H is equal to 1.2a. Okay, so this is very nice question. Actually, we have to just read one by one, and let me get this figure in the next page also, so that we can answer here with reference to this figure. See, the option is current in wire 1 and wire 2 are in the same direction. Okay, the question was, so the situation is that, so there are two parallel wires, so wire 1 and wire 2. This is a PQ and RS. Actually, we need to find out the direction of the currents in both the wires. See, look, the question is here is that when D is equal to A, the wires are not touching each other, touching the loop. It is found that the net magnetic field on the axis of the loop is 0 at height h above the loop. Okay, so the magnetic field at height, see, if I just take the loop itself here like this, and see from above, okay, above, this is the height from the center is h. Okay, all right, we can just take that, or let me just draw it little more clean. Let us go like this. Sorry, this will be perfect. Okay, this is the one, and this height is actually h. So at this particular point, this is actually on the axis. So this is axis of the, this is the axis. If I just give some name, arbitrary, OA or OP. So this is okay, P is there. Anyway, we don't use this. OX, let us say. So OX, this is the actually axis of the loop. Okay, and see, now this A is equal to D. A is equal to D. That is also given. Anyway, the question is now, see, the wires are just beside this. Okay, just beside this they are going. Okay, PQ, Q, this is P. So these are the wires as you see in the figure. Okay, so this A becomes just D. That means not exactly touching the loop, but it becomes, see how what it becomes, the wires are actually very near to this. Okay, like this. This is PQ, and this is RS or SR as you read. Okay, this is W1, wire 1, and this is W2. Now look, this is A or whatever you can take. Okay, D or A, both the same actually here now. All right, see, actually there are two things. the magnetic field will be produced by this two wire at this particular point, okay, at this point, or if I take this point, magnetic field will be produced by both PQ and RS at this particular point, and also it will be magnetic field will be produced by the loop. See, magnetic field produced by the loop will be always in this direction. We know this, right? Magnetic field due to loop will be always along the along the axis. Okay, so magnetic field will be always along the axis. So it will be actually OX direction. So the magnetic field has to be zero at this particular point P or at particular height H only when the magnetic field produced by these two, this PQ. So magnetic field, let us say magnetic field produced by wire 1 is written as Bu1, and magnetic field produced by the wire 2 is written as B2, okay, and magnetic field produced by the ring is Br. Now, according to the question, at this particular point, net magnetic field will be zero only when the resultant of this or resultant of this two magnetic field will be exactly equal to the resultant of the magnetic field produced by the ring. Now look, in this case, obviously the magnetic field has to be, the magnetic field produced by these wires must be along this direction, okay, right? So I hope you have understood this. So magnetic field has to be produced by this way, in this way, okay, produced in this way, okay. So we can now, so we can just actually calculate magnetic field due to see there is a wire like this here and another wire is this here, and these are actually going into the plane of the paper, that you can understand, okay, because they are perpendicular to the plane of the loop, and these will produce magnetic field. Now we need to just, let me not give this signs. So we need to find out the way how the magnetic field uh, or the current, sorry, in which direction the current will be in wire 1 and wire 2, okay. So wire 1 should actually carry current. See, at this position, if I have to have magnetic field due to this in the low, in this direction, okay, you know, if we use the Biot-Savart law, so suppose this is R, so this distance is R, and from here also this distance will be R only. So these are two wires, okay. Now magnetic field, both are carrying the same current, so magnetic field produced by both of them will be the same, okay. Magnitudes are same actually. So magnet is, if I say these are theta, these angles are theta, then so the B1 is along this way, B2 is along this two, okay, this point. Now here actually the current has to be in such a direction that magnetic fields are in this, okay. So you look here, option C, current in the W1, wire 1 and wire 2 are in the direction PQ and SR, PQ and SR, PQ and SR, PQ, PQ and SR, okay. So PQ, if the current goes in this direction, okay, so what will happen? So magnetic field will be produced due to this actually go into the plane of the paper, and if this current goes this way, so it will give you the magnetic field in the direction this out of the plane of the paper, okay, out of the plane of the paper magnetic field will be there, and their resultant will actually give you the net magnetic field that will be exactly equal to the magnetic field produced by the loop. Okay, so let us do this. B1 and B2, they will be actually, since it is long wire, mu0 I by 2 pi d, 2 pi and d. Okay, mu0 I by 2 pi d, 2 pi r or d. Here actually, let us say this distance is r only, so this is r. Here in fact r is equal to a only. Sorry, no, r is equal to this one. Okay, this one, this is the r. We are actually calculating magnetic field at this particular point h. This is actually a point here. Okay, so that's why this is r, we have to take magnetic field due to this is r. Anyway, now this is due to 2, so if I just take net magnetic field, now what is the net magnetic field produced by the wire? b net will be the resultant of b and b1 and b2. Resultant of b1 and b2 will be the magnetic field. Okay, so 2 into this, okay, so this is going to be the, here there will be cos of theta, because see we will have component in this direction. So maybe I'll just erase some of the things so that it becomes little visible, or let me just draw in the next page. Okay, let me just make it a little visible, more visible. Okay, so as you see, this is the height h, and this is one angle, and this distance is r. Okay, this is the r. So r will be actually r square is equal to a square plus h square. Okay, this is the r square. Okay, so here this is c, there will be two components along this way. So b1 cos theta plus b2 cos theta, sorry, yes, b1 cos theta and b2 cos theta. So b1 cos theta and b2 cos theta, if we add them up, then we get 2 into mu0 I by 2 pi r into cos theta. So cos theta, again cos theta is equal to base by hypotenuse. So base is h, hypotenuse is r. So you get mu0 ih by pi r square. Okay, so mu0 ih by pi r square is the magnetic field produced by these two wires at this particular point. Okay, all right. Now this magnetic field will be actually exactly equal to the magnetic field produced by this loop. What is the magnetic field produced by this loop? We know that the BR will be along the upward direction, and it is 2a square, 2a square, 2a square mu0 into I, mu0 into I, 2a square. Okay, there will be obviously a pi mu0 I into pi a square. Okay, so due to this is actually mu 0 I pi a square divided by a square plus h square 4 to the power 3 by 2. Okay, so here there will be obviously a 2. Okay, 2, and pi actually will go off. This pi and that pi will go off. So mu 0 I a square by 2 a square plus h square 4 to the power 3 by 2. Okay, so this is how we get the magnetic field due to the ring. And now look, I'll just write it down whatever we get. So B net we have got, that is now the magnetic field due to the loop or ring will be, this is mu 0 I h by pi r square, and that we know mu 0 I a square by mu 0 I a square divided by 2 into x square plus, sorry, a square plus h square 4 to the power 3 by 2. Okay, so this is, and they will be actually exactly equal to each other as I have shown in the figure like this, right? So loop produced magnetic field this way, and they are resultant of this, resultant produced by these wires has to be this, and they will be exactly equal. Okay, so B net is mu 0 I is h pi r square is equal to this ring will produce magnetic field at the center is mu 0 I a square divided by 2 into a square plus okay. So this is the thing, so we'll get to, yes, all right. So doing this simplification, what we get actually, we'll get, if you just solve it for h will be exactly equal to, the 1.2a. That means the magnetic field will be 0 at height h is equal to 0, sorry, at h height is equal to 1.2a. So that particular height, the magnetic field produced by the loop will be exactly equal to the equal and opposite in magnitude of this net magnetic field produced by this wires 1 and 2. So this is the height h. Okay, so we have had these options. You can see that the current direction we have to first of all find out, and then when directions are done, now you have to find out what is the value of h where the magnetic field is going to be 0. So that is what it is. So the option C is correct answer for this question. So currents in the wire, the last option was current in wire 1 and 2 are in the direction PQ and RS respectively. No, it is not RS. One is along PQ direction, another one is SR direction. Okay, that means it goes like this, coming out, and this. Okay, according to this question. Now we'll go to the next problem. Okay, so one more problem was there related to the same figure. Related to this same figure, the question I'll be writing here related to the same figure. See, the question was consider D is much greater than A. D is much greater than A, and the loop is rotated about its diameter, and the loop is rotated, and the loop is, sorry, and the loop is rotated about its diameter, the loop is rotated about its diameter parallel to the wires, that means the diameter is parallel to the wire by 30-degree angle. Okay, from the position shown in the figure, from the wires. Now, if the current in the wires are in the opposite direction, so if the current are in the opposite direction, in both the wires, the torque on the loop in its new position, the torque on the loop at on the loop at its new position will be that means we have to actually find out the currents. So if the currents are in the opposite directions, the torque, you have to find out the torque on the loop at its new positions will be torque. Okay, the options are given as A, mu0 I square A square by D. Option B says it is the same thing, mu0 I square A square by 2D. Option C says it is square root of 3 into mu 0 I square by D. And what about the option D? Option D is like same thing. It is root 3 into mu I square A square by 2D. Okay, so these are the options, and you have to find out the answer for this. See, actually the magnetic field at the midpoint of the wire is how much? That is, for the first one is, so magnetic field due to, okay, just a minute, I'll get some pages in between. Okay, so the magnetic field at the midpoint of two wires would be how much? Magnetic field of two wires magnetic field d2 wires at their middle point, actually due to the wires at the middle point of the wires actually will be, and that is given by mu 0 I by 2 pi d 2 pi d mu 0 I by 2 pi d, and we have to multiply 2 here for two wires. So this is the magnetic field produced by both the wires. Okay, so this will be actually mu 0 I by, okay, so this is pi d, mu 0 I by pi d. Now what is the magnetic moment? Actually torque means actually m cross b, or mb sin theta. So we have to first find out what is m. We have got the b anyway. M is the magnetic moment, which is I into A, and that the torque on the loop will be actually how much? The theta is actually 150. Okay, direction of the torque with the field. Okay, so it is actually torque is mb sine theta 30 degree, or you can write mb This is 150. We know this is mb sine, sorry, this is actually mb sine theta, right? mb sine theta. So we got it, mb sine 150. We can write it is in the same way. All right, so now we can actually put the values. We have got b, we can put the value. The torque mb, m is I into a, and b is, this is m, I into a. Okay, and b we have got mu 0 I by pi d. Okay, now torque will be found out. So we get, so mu 0 I square, mu 0 I square, then a is actually pi a square. So mu 0 a square, I square a square by 2d. So this is the expression for the torque. Okay, this is the expression for the torque. Okay, so this question is done. We'll go to the next question. So here, two infinitely long straight wires lie in the xy plane, okay, along the x axis, sorry, xy plane, anyway, xy plane along the x axis, and where the x coordinate is plus minus r, the wires located at x is equal to, the wire located at x is equal to plus 4 carries constant current I1, and which is located at minus r, that is carrying a current I2. These are I1 and I2. So I1 and I2. A circular loop of radius capital R is suspended with its center at 0, 0. This is square root of 3 r, and in a plane parallel to xy plane, the loop carries a constant current I, and the current is flowing in the loop in the counterclockwise direction as seen from the above of the loop. The current in the wire is taken to be positive if it is in the positive j direction. And which of the following statements regarding the magnetic field is or are true? I'll just go to the figure right here. See, there are two infinitely long parallel wires. One is located at x is equal to minus r, another one is located at plus r distance from the origin, and these are in the xy plane as you see, and there is a loop which is located at this coordinate 0, 0, 0, 0 and root over 3r. This is the center of the loop, which is located from this origin at 0, 0, root over 3r. So this is the question. Okay, this is the fact. Now the loop carries a constant current I. Loop carries a constant current I, whereas these two guys actually are carrying different currents, I1 and I2. So this is I2 and this is carrying current I1. Okay, the loop carries, okay, fine. The current in the wire is taken to be positive if it is in the positive J direction. Which of the following statements? Okay, I'll tell you the statements. The first statement is saying that if, okay, if I1 equal to I2, then B cannot be equal to 0. Cannot be equal to 0 at the origin. Okay, this is first option. Let us just try to solve this, or try analyze this option itself. Look, look this. The question is that at this particular position, the magnetic field should not be 0 at the origin. Magnetic field cannot be 0 if I1 and I2 are equal. Okay, you don't know the direction. So at the origin, see, if the magnetic field has to be 0, what are the things? If magnetic field at 0, 0, 0 or at origin has to be 0, then look, the magnetic field produced by and magnetic field produced by this wire, they have to be actually, see, since they are equal and opposite, so either what, if it is to be 0, then what happens? Actually this I, see, anyway, the magnetic field created by this particular wire at this position will be in the upward direction always. Okay, and the magnetic field produced by this guy, this wire, will be in this direction. Okay, in this direction. All right, since they are in the xy plane, since they are in the xy plane, this is, anyway, this is x and this is y. So the wires are in the xy plane. So that's why the currents actually, see, if they are same, they will cancel each other. They will cancel each other. The magnetic effect of this current, these two currents will be actually cancelled by both two. Okay, both of them. But magnetic field produced by this guy, this particular loop, see, it is in the opposite direction actually. It is in the opposite. Since it is in the clockwise direction, magnetic field produced by this loop will be in this direction. So at this position, there will be non-zero magnetic field. Okay. The option was that if I1 and I2 are equal, then B cannot be equal to 0 at this. Actually, this is, it is actually true. It is true. So this cannot be 0. This is true actually. This is true. Now the next option, let us see. Next option says if I1 is greater than 0, if I1 is greater than 0 and I2 is less than 0, that means it is positive, this is negative, then B can be, magnetic field B can be equal to 0, at the origin, at the origin 0, 0 and 0. Okay, look now, go to the figure, this figure. See that the question is now, if these two guys are, so this is I2 and this is I1, if one is positive another one is negative, then what happens at origin? See, the magnetic field produced due to wires will be, see, if the current is negative, that means if it is in the negative y direction, okay, and this is positive y direction. See, if it is positive y direction, then a magnetic field will be plus k direction or in the positive k direction due to wire 1, and magnetic field due to this wire 2 will be in this direction again. Sorry, this will be again in the same direction. I'm sorry, this will be in the same direction. Okay, so both of them will be in the same direction. Magnetic field produced by the wires will be same in the positive y direction. Okay, positive, sorry, k direction, not y, positive k direction, as you see, like this. Okay, this is origin. Okay, and magnetic field due to the loop is always in the this direction, because it is current is in the clockwise direction, so magnetic field due to this loop is in the downward direction, that we see. And there will be a possibility, okay, there will be a possibility of having zero magnetic field. Okay, hence magnetic field can be zero at origin. Obviously that depends on this value I1 and I2, but there is a possibility. Okay, so if these are this, so B can be equal to 0 at the origin. So this is actually true. Okay, this is also actually true. There is a possibility. Now the third option says, with the same condition, if this I1 is, sorry, I1 is less than 0 and I2 is greater than 0, that means one is positive another one is negative, then whether the magnetic field at origin will be 0. So that is the option. Now let us see the figure. Where is that? Okay, the figure is that here. See, suppose this is now in this direction, positive y direction, and y1, sorry, I1 is in this direction. So it will be actually producing magnetic field. So this wire may produce magnetic field B1 in this direction, and magnetic field due to this will be, so again both will be in the same direction, that is in the negative y direction. So due to the wires, magnetic field will be in this direction, negative k direction, and due to the loop also magnetic field will be in this direction. So this is actually, the option was that can be 0. No, it is actually at the origin magnetic field will be along negative k direction, and due to loop also it will be negative k direction. So this is not true. It is actually false statement. Okay, this is not true. The last option we'll see. The last option is, if I1 equal to I2, then z component of B at the center of the loop, at the center of the loop, center of the loop is minus mu 0 I by 2r. Okay, so this is actually option D. See this position, this center is actually 0 0 root over 3 into r, so it is not very difficult to calculate the magnetic field. Okay, so look, what we can do is we can see here both are actually in the same direction, say. So here if I just add these 2 points, these 2 points, sorry, this one, so the magnetic field at this, okay, so this is r, magnetic field is this way, so this is B1, sorry, B2, this is B2 because the current is I2, and here it is B1, okay, because the current is I1 here. Okay, now what is happening, that the magnetic field, oh I'm sorry, not this, just a minute, see, we'll just draw this point, this is the center. Okay, so these are the 2 wires over here. Okay, so the magnetic fields are like this, B2 in this direction and B1 is in this direction. This is the Z axis. So there, see there, if we take their components, see there will be magnetic field along x direction because this is x direction. So at the center of the ring, magnetic field due to the wires will be along the x direction. Okay, hence the magnetic field due to magnetic field at the center will be only due to the loop itself. Okay, so we can see the magnetic field due to the wires will be along x direction. Okay, this is magnetic field due to the wires will be along x direction. So the magnetic field at this center of the loop will be only due to the loop, and it is actually along this direction, minus k direction, that is true. Okay, magnetic field at the center of the loop will be along this, and let us say bz into this. Okay, so what is this bz? We can just calculate. Bz will be, see, at the center, right? So we know it is mu 0 I square by 2 into a square plus x square due to a loop. So this x is 0 here, so it will be mu 0 and whole to the power 3 by 2, right? So mu 0 I square divided by 2 into a cube. Okay, so this will be exactly mu 0 I by 2a. A is here, actually the radius of the loop is r, so we can just write it mu 0 I by 2r. Okay, so this is the magnetic field at the center of the loop, and the direction of the magnetic field will be in the negative k direction. So the option was this, mu 0 I by 2r. So this is correct. Okay, so this D option D is also correct. Only option which was not true is that the C, which is not true. Otherwise A, B and D options were true. This is true actually. Okay, this is also true. Magnetic field at this center will be only due to the loop. Okay, so with this we'll stop it here for today. We'll pick up nice questions again in the next class. So thank you for your patience. Bye for today.